So for those of you who are familiar with our software ATENA, we focus in modeling of concrete structures. We are using nonlinear approach in order to be able to estimate the real concrete behavior, the real behavior of concrete structures, for which we need to include nonlinear material behavior, such as crushing of concrete if it's under substantial compression load, or cracking in tension and softening behavior of concrete material, or when it comes to reinforcement. Our software can estimate yielding of reinforcement, or which is the topic of today's seminar. It can estimate the slipping of reinforcement bars with respect to the surrounding concrete. So the scope for today, I will start with basic introduction of reinforcement modeling in ATENA to give us some common ground, some theory of the implementation of reinforcement in the software. And then I will move to modeling of bond, which is characterized by cracking of concrete, and then modeling of bond by slipping of reinforcement with respect to the surrounding concrete. I will show some code-based bond laws which are implemented in our softwares, and I hope there will be time for 2 examples where I will show how to use our software. What are for example, some handy plots for your results, and how to pre-process and post-process your problems. Some basic introduction why modeling of reinforcement bond is of a great importance for us as structural engineers. Here you can see 2 models where the maximum pullout load is determined by modeling some small portion of concrete block, where is with some anchor in here, and applying some pullout load in this direction, we can determine what will be the maximum load and also the failure mode. Here there are two ways how to model it. In one way the reinforcement is modeled using 1D compression tension element. Here we have a full 3D model where also the reinforcement is modeled as 3D with 3D solid elements. Here you can see that in this model the failure mode is yielding of the anchor, as indicated by the plastic strains on this image, or on the right image we can see some necking behavior of the anchor, because the 3D elements then they can nicely display this kind of behavior. However, for today we will be focusing only on modeling in this approach where the reinforcement is represented by 1D elements. Those 1D elements, they are this kind of basic reinforcement type in ATENA. They, as I mentioned, they only work in compression and tension. They cannot transfer any shear forces or bending behavior. They are kind of easy to use in the software because you model them as line elements. You place them inside of the volume elements, and the software will automatically identify them, mesh them, and connect them with the surrounding concrete. So from this point of view, they are very easy to use. They can be used also for not only for modeling of common reinforcement, but also for modeling of pre-stressing cables, etc. We will be preparing a separate webinar for this topic, where we be focusing on modeling bond for external or internal cables. However, for today we will focus on reinforcement with no pre-stressing. So, for example, consider that I have a model, this kind of a L-shaped beam, and I place the reinforcement inside of the concrete volume. When I look from the top on my model, and maybe this is not so realistic, but for the sake of this example, the reinforcement bar, as indicated here, is this kind of curved in the corner. So from the GID preprocessor, which is used to use for the modeling and generating the input files for ATENA, I will probably get this kind of 4 points connected by line elements, and the meshing from GID will be probably this kind of 3 elements. And once generated the input file, the software will automatically generate nodes at the boundary of each finite element, each concrete element of the model. So of course the nodes will be at both ends and at the points from GID, and then at the boundary of each element, as can be indicated here. So this is my concrete element, this is the reinforcement inside, and at the boundary, the ATENA kernel before the solution start will generate nodes for the reinforcement. The displacements and the nodal coordinates of the reinforcement are bound with the surrounding concrete with some shape functions, and their displacement can be expressed as a linear combination of the displacements of the nodes of the surrounding concrete. This is just to show some background, what is happening, and how to determine the displacement during the solutions. So, and get back to the topic for today, which is some kind of how the reinforcement and the concrete carries the load together. So this kind of continuity of strains can be the discontinuity can occur basically from two reasons. Once, if the surrounding concrete is subjected to some stresses which can no longer withstand, there will be a crack appearing in the element. So, for example, if we imagine this kind of element being and the tension applied to the reinforcement inside, it will also create some kind of tension in the element. The element will finally crack, and discontinuity in strains will occur. That's one reason, and the second reason is that if I have some kind of cable or reinforcement in the concrete, and I have a poor quality of the bound, then some slippage can occur. Can occur some slippage of the nodes with respect to the surrounding concrete can occur. In the ATENA software, this is implemented through adding one extra unknown, one extra degree of freedom, which is the slip of the reinforcement. So you can imagine that on the reinforcement bar inside of the concrete, there's at each node there is one additional degree of freedom, one kind of interface, which represents the interface element. Or in general case, we are looking at and comparing the forces between the concrete and the forces at the interface. When if I have this kind of bar and which has some given length. And I have a force at two ends, and the force is different, then it means that to have the equilibrium, that this this difference in forces is compensated by some cohesion force, which is transferred to the around the area of the reinforcement to the concrete through the cohesion stress. So maybe at the beginning I forgot to mention that that also you, if something from my explanation is not clear, please do not hesitate to ask the question. You can either the best way how to do it is to type it to the chat window, to the chat box, and I will be checking the chat window from time to time to or my colleagues, they will try to reply the messages as the presentation goes on. So back to my slides. First, I will explain shortly how to model how ATENA can estimate the bond properties, or how to model the bond by cracking the concrete. Even though that I don't define any bond slip law for my material, ATENA can still estimate the bond behavior. This is simply due to the fact that in many cases the bond is actually the stronger part of the system, and the weak link can be the surrounding concrete, which will crack before the slippage of reinforcement occurs. Actually, this is the case of, for example, reinforcement which have hooks at the end. This is common in probably, as you know, in some seismic areas where, or for example, if I have a threaded rod inside of concrete, or also in many cases this will be the case for common ribbed reinforcement. Here you can see two examples of such a modeling. One is a pullout test, and one is this kind of pre-stress concrete beam. Here, this line represents the cable, which is through initial strain pre-stressed, and here at the ends you can already see some cracking. which is compensated by releasing of the stress which is the reason for some stress decrease at the ends of the bar. Here you can see some so what actually happened inside of the concrete during the pullout test. On the left image, you can see how the cracks occurred if the pullout load is applied to this end of the reinforcement. Firstly, some cracks form around the bar, and then kind of like splitting failure mode occurs with formation of a continuous crack along the reinforcement, and at the peak load this crack is continuous, and the element can no longer, and the element breaks and can no longer transfer higher load. Here on the right image, you can see how a cone forms, like this kind of typical cone is activated around the reinforcement, and finally at the same moment we can see the splitting of the concrete. Here some more about the cracking around reinforcement. Here this is kind of a T-beam with 3 cables at the bottom of the beam, and if the pre-stressing strain or stress is increased, firstly we will see some formation, crack formation at the end, and if we ignore it and keep increasing the stress, it will finally lead to formation of the continuous crack along the length of the reinforcement. You can see that the characteristic shape will collapse. We will lose the continuum bound between the elements, and so this is kind of a of course something we don't want to happen. We don't want to occur. So even this kind of problems can be modeled using ATENA. So this, until now, I was talking about examples where the bond between the concrete and the reinforcement is perfect. We don't assume any bond slip law for the nodes of the reinforcement and concrete. However, in many cases we need to assume this one because the bond is not perfect. There can be some after we increase the force, there can be some slip between the node of the reinforcement and the surrounding concrete. This can be inputted into the software in kind of a bond slip law, where which is basically a cohesion function, which depends on the slip. Then during the solution, we firstly check if the stress in the reinforcement node exceeded the cohesion. This is done through this equation, and at this moment it is important to realize that for the reinforcement bar, this equation is evaluated at each single node. So for instance, for this node, I have one force in the reinforcement from the left side, another one from the right side, which is the left-hand side of this equation, and the slipping occurs if this force, if the difference of these forces is higher than the cohesion along the reinforcement. For this node, the cohesion force will be calculated in 1/2 of this section and another and half of this section. So here we are basically integrating the stress along the perimeter of the bar, along the length of the bar, from 1/2 of the length of each element on both sides of the node where we're evaluating the cohesion force. And if we in this step the slippage occurs, we are trying to find an equilibrium. For this at this point there will be two additional parts of this equation, which is this part and this part. They can be seen somehow like some kind of like a reinforcement relaxation due to slippage. K here means the actual stiffness of the bar, and here this is the slip. So the slip is at this moment the unknown for us, and once we find the equilibrium, we know how big the slip is. So doing preprocessing, what I need to do if I want to apply the model. Here there are two windows for those of you who are familiar with the GID software. You already know them from defining common reinforcement. So the bond behavior is available for so-called bar with bond geometry type, which you can find in the element geometry tab. And there are several options which need to be specified. At the beginning, the option bar end specifies whether the end nodes of the reinforcement are fixed with respect to the surrounding concrete. For example, this is useful for, as I will show later, for modeling of the pullout experiment or for modeling hooks at the end of the reinforcement in many structures. This simply says whether the end node can slip or not. If we fix it for the last node or the first node, the slip function will be not applied. Then of course we need to know the bar perimeter, which is of course dependent on the radius of the reinforcement. The maximum bond strength, and then the function of the bond strength as with respect to the slip. This function, it is inputted as a relative function. So the maximum bond strength in here is multiplied by this function. So the units of the slip is the unit which you are using for your analysis. In most cases, it will be meters, but in GID you can also switch to another unit system. So based on this unit system that you choose, the units of slip should correspond to this chosen unit system, and the bond strength is relative with respect to the maximum bond strength. Also for the for this function, there are some dependency functions available. If you, for example, you have for your static analysis, you have as an input some temperature distribution in your structure, which can be used for for example, evaluating the structures under some fire conditions. You can use some temperature dependency for the bond slip function. It will be also a relative function which multiplies the maximum bond strength. Or for durability studies, as you know that we in ATENA, you can, for example, apply some chloride attack condition on your structure, or carbonation carbonation deterioration, which will induce corrosion of your reinforcement, and the bond strength can be also reduced by this kind of as a function of the corrosion. And finally, there is location dependency, which for each bar can determine along the length of the bar whether the how strong is the bond along the bar. So it can be with this function, it can be even deactivated at some part of the reinforcement. During so one last thing which is defined during the reinforcement during this preprocessing is the function for bond slip law. In GID, there are three literature or code-based functions implemented, for which if you input the strength of your concrete, then you can and type of the reinforcement, this kind of function for bond slip will be automatically generated for you. It should be noted at this point that these functions, for example, from the FIB model code, they already there is already some impact of cracks, so you need to be careful not to include this, let's say, twice in your model. These functions are very much suitable for modeling with using, for example, shell elements, or generally for the cases where the condition around the reinforcement are not so well described by the model itself. However, even if you are using solid elements and modeling some micromechanical problem, you can use this kind of bar with bond function and calibrate the function for bond slip based on your experimental data. So I think now we are somehow around the middle of our presentation. And we will move to some examples. I will check if we have some questions until now. Okay, now I can see the chat window. So as Tambusai asks, very interesting topic. I'm particularly interested in bond modeling for corrosion. Would you be able to explain input-wise procedure for this use, as there is no any quick generation as in the general bond using model code? Yeah, I will quickly give a comment on this one, but actually we are preparing a separate webinar for this topic. It will be it is scheduled for maybe next month. But generally the procedure will be that you will find some literature data or your own experiment data, how the bond is reduced with respect to the reinforcement corrosion. In for your model, you can directly apply some corrosion phenomenon on the model, either as a chloride induced corrosion or carbonation. And based on this, ATENA will automatically calculate the reinforcement corrosion, and through this dependency, which is inputted as in here as a relative function of the corrosion degree, the bond will be reduced. Or if you I can imagine that you don't want to go into the modeling of the deterioration mechanism. I mean the chloride ingress or the carbonation, and you directly want to simulate the impact of the reduced bond. So in this case, I think the best thing would be directly input the reduced function here for the function for bond slip. So if you have the function for different corrosion degrees and just simulate the pullout load experiment, you can directly input it here and see how it affects your result. So another question for Zachary Coleman. Can ATENA model non-perfect bond condition for hooked bars? If so, does ATENA model model the end bearing of the hook on the concrete or only the bond stress? Yes, of course. It can be done. Around the hook, the stress will be also transferred to the concrete through compression, or not just along the reinforcement. So the hook will create some. So in this way, the hook behavior can be modeled. For these cases, actually, if you focus on this kind of detail, I would suggest to model it to model the reinforcement as a 3D with 3D solid elements. And between the concrete and the reinforcement, use some interface element to model the bond. Is bond along polyline same as straight bar? That's another question. Yeah, this is very similar actually, and I will be talking in more details about this in one example. And what does the parameter embedded reinforcement represent? Does it depend on the meshing size? I'm not sure now what this is referred now. Where the embedded reinforcement parameter, where this embedding is specified as a parameter in the software. I forgot now. Yeah, it is.
Sorry to interrupt. It's not about bond. It's about element geometry. The option in element geometry.
Okay, the option in element geometry. This one. This size. Yeah. Thank you, Muhammad, for explaining me. This actually specifies the shortest distance between the two nodes of reinforcement. As I mentioned, that before solution of the before the actual solution starts, ATENA kernel generates the nodes along the reinforcement, and this is the minimum distance between two nodes. If from some reasons the node should be closer from each other, there will be only one node generated. So this is the meaning of this option. So let's move on with the presentation. I will show now two examples. One is beam underbending with bond reductions. These examples, they usually come from our users who try to simulate some problem, and sometimes and as you probably know, if you are a user with valid maintenance, you can send us an email, and we will try to help you with your modeling. And often there are questions about some models that for example, I have this kind of simple beam, and I try to reduce bond in the midspan of the beam, and I check my LD diagram to see what happens. And sometimes it can be that, for example, the engineering idea is different from the results, which was in this case where it was expected that if I reduce the bond in the midspan, for example, to just 5% of its original value, it will somehow I should be able to directly see it on the LD diagram, or there will be some significant impact. So let's see what happens in this kind of case. For this model, there was some general bond slip law applied, and this 6 reinforcement bars were used, and this bond slip law was applied to these 6 reinforcement bars. The ends of these bars were fixed with respect to surrounding concrete to simulate the hooks at the ends, like if we are in some seismic area. And through the location dependency function, the bond was reduced in the midspan. The total length of the beam was 6 meters and 5 meters. And for the 5 meters in the midspan, the bond was reduced. Several cases were analyzed, either with a full bond or 75% of the initial bond, 50, 25, 10, and 5% of the initial bond strength, and which means that the bond slip function was modified in this kind of way. So, and the LD diagram, we can see what happens with the beam. Only if the bond was reduced below, let's say 25 or 10%, we can see some significant impact on the LD diagram. Before that, the only some small reduction of stiffness was observed. Also, the peak load was similar, and also the failure mode. It was always the yielding of the reinforcement. We can see some small impact at the moment of when the first crack occurs, and only if the bond was reduced to the 5% of its original volume, we can see different failure mode, which was some crashing of concrete between the crack and in the compression area of the beam. From some easy engineering representation, basically what we did was simulating this kind of problem. Even it can be seen that there is no bond in the center, but what do I need to transfer the moment load? I need the compression area. I need the tensile. I need the reinforcement to transfer the tensile loads, and then I'm fine. Probably if I try to shrink the beam, make it shorter, then there will be some significant impact of shear forces, and for this the reduction of the bond is more sensitive. But in the bending behavior, we don't see much. But if we want to analyze the results in more detail, here we are looking at the reinforcement from the top, and we can see that if we reduce the bond strength, the longer length of the bond will be activated, which is indicated by this kind of figure. We can see how the distance of higher stresses gradually increases with the decreasing bond reduction, and this will also somehow affect the cracks in the beam. When there is a good bond condition, there will be more cracks, which will be smaller in size, smaller in width. However, with the reduced bond, only a few cracks will localize, and there will be of wider width. This is somehow similar to what we observe when we use less reinforcement of higher diameter, comparing to many reinforcement bars with smaller diameter, in case that the reinforcement degree is the same. The important fact is here that the reinforcement is fixed at the supports. This is and so there is no slip at the ends of the reinforcement, which in here it's no problem, because and also in the engineering practice, the codes always tells us to have the ends of the reinforcement in some compression zone, so it's somehow constrained and slipping is not allowed. So now I will move to a second example, which we also get a lot of questions how to properly model it from our users. This is somehow simplified modeling of pull-out load experiment. We can see we can see here the components of this model. The model is composed of some concrete cube, of reinforcement bar, some loading cube, because as I mentioned at the beginning, the reinforcement 1D link can only transfer tension and compression forces. So so it always needs to have at least the ends embedded in some solid material or 3D material. So that's why there is not only free end, but also there's some kind of loading cube or loading plate on which we applied the prescribed load. Then the model and the supports of this of the concrete are modeled through some loading plates on which we apply the constraints. And based on my understanding, this kind of experiment usually ends up in three possible scenarios. Either if the reinforcement is too weak and I'm too strong, I can rupture it. It will first start yielding, and then I will the rupture of the reinforcement will occur. Or I can, in case that it's a larger experiment, I will pull out some concrete cone, or in this kind of small cube, probably there will be some splitting failure mode, as I showed previously in the presentation. Or if the bond between the bar and the concrete is not good, or which can be, I don't know, I can think about some poor compaction of concrete, or probably for bars which don't have any ribs, this can occur. I can the length, the embedded length of the reinforcement is only short, then I can pull it out from the concrete. So that's my expected 3 types of failure mode. So before we figure out how to what happens in our case, I will explain how to model it. So in this case, I have 10 centimeters of the reinforcement in the concrete, and the rest of the bar is not embedded. And on this part, I want to apply the bond slip law, and on this part of the reinforcement, should carry no stress, which means that before I get there, how the mesh will look like. So these black dots, they represent the nodes of the reinforcement. ATENA automatically place them at the boundary of each element at the ends. So the endpoints are here, and then at the boundary of each element. And my goal is to have this kind of a boundary node and have two boundary nodes close to each other. What it means that, as I explained earlier, the cohesion force is always evaluated from half of the reinforcement of the element length on both sides of the node. So in this node, it will be from this part and also from this part. And it would mean that if I have a node for which the bond is activated just at the boundary, I will also have the contribution of half of this free end of the bar. Basically, this node doesn't know that that the length is not embedded here. So it will. so my result will be affected by this inaccuracy. Therefore, I activate the bond only for this node up to the not for the last one, but the one before the last one will be still activated. I will have the contribution of half of this small section, and for the last node, for the boundary node, the location dependency function is not activated. Therefore, at this node, I will not calculate the cohesion force from this free part of the reinforcement. Also, I should, although that the length of the bar is this size, I specify the location dependency function a little bit longer, because due to the pooling of the reinforcement, there will be some second order effects. This node will slightly move, and if I just input this value here, it will happen that this node will be a little bit beyond this limit, and it will not be included. So even second order effects are implemented in this kind of function. So in GID, what I will do is that I will mesh this reinforcement as a polyline with one node just before the end of the concrete cube. My goal is to have two linear elements from the mesh in GID, one in here, one in here, and then when it's sent to ATENA Studio, how to do it is we edit this kind of setting for polyline, select the polyline, and force GID to make it two segments. And then when it's sent to ATENA Studio, before the solution, the nodes will be generated in this manner. Finally, for this polyline, I will have the same settings. This will be one material applied to the polyline, and the last thing to set in the material settings is to fixing this end node with respect to the loading plate. So for this, I need to check the orientation of the line, because as you know, each surface and each line in GID have their orientation. So this little dot indicates that the start is here and the end is here. So I choose a fixed end. So then in the post-processing, I should see some kind of a figure like this, that the stress is correctly applied only on the portion which is embedded in the concrete. And here I have no, on the free end of the bar, I have no stress. There is some little inaccuracy in here, but if the distance between the two nodes at the boundary and the one before the boundary is sufficiently small, this inaccuracy can be neglected, and we are basically obtaining the theoretical solution. So after simulating this, I will be probably checking my LD diagram, and my next question might be, what's my failure mode? Looking at this one, probably we all know what is happening, because we can see some characteristic shapes of the relationship between the pullout force and the displacement. Here I show the three possible outcomes which depend, and it will depend whether I have on my concrete properties, on my reinforcement properties, or on the cohesion, which one of these will be my final failure mode. To see what is happening in my model, for each failure mode, I should probably observe some different variable. The most important one, which is important, will be the crack pattern and the deformed shape. For the concrete splitting failure mode or concrete cone pullout, I should see some activation of the material along the whole length of the reinforcement, which will be accompanied by some substantial cracking around, and also I can nicely see how the crack opens on the different shape, that the longitudinal crack opens, and I can see the splitting. While when we compare it to the rupture of the reinforcement, we see the deformation accumulated in the length of the reinforcement, with only fewer cracks inside of the concrete volume. And if we plot the reinforcement strain in the bar, we should see this shows 3%, and in the model there was this European grade A type of reinforcement which ruptures at 2.5%. So we can see that we already exceed this limiting strain. So this will give us the red shape, red failure mode indicated in the LD diagram. Or if we if I define some bond behavior, I should be able to see, if I plot the bond slip data, that I'm already behind the peak of my defined bond slip law. Final slide of this presentation, just to compare the two. As at the beginning, I was explaining about simulating the bond slip as a function of cracking of concrete. So if I compare it with a function where I have some bond slip defined, then I'm comparing this black and green curves, and it shows some general trend. If you apply bond in your model, you usually slightly reducing the peak load and reducing the stiffness of your model, because you are the additional degree of freedom, the slip along the reinforcement, it adds some additional compliance in your model, which affects the stiffness. So with this, I would like to end this presentation. Thank you for your attention. We are slightly running out of time, so I, of course, I'm sorry for this, but maybe I can still answer some of these questions which accumulated here, maybe shortly in the last 5 minutes of the presentation. So yeah, we can see the Mohammed wrote the email address for our hotline support, and the ACI code bond slip parameters. We have currently there are three different bond slip laws for generating in the newest version of ATENA 5.9, and those are the two FIP codes, model code 2010 and 1990, and the big guy model. Then it was Mohammed explained how to check the orientation of the normals for the reinforcement bar. Could you explain how to use the location dependency function to apply the bond law only to a portion? Okay, so I will get back to that slide. So in here, my goal is to apply the location dependency on this polyline, on this reinforcement, which has this total length of 0.35 meters, and I want to apply it only to the portion embedded in the concrete, which is 0.1 meter long. So the function will look like this: that at the start of the reinforcement, which I determine by the orientation of the polyline, I know that this is this point. So at the location 0, my coefficient, my relative strength of the reinforcement is 1. Just before the boundary node, I still have which is 0.1 millimeter before the boundary node, I still have the relative strength 1. And for the boundary node, I set the, which is 0.1 meter. I switch the relative strength to 0 and keep the strength to the end of the reinforcement, which is this last point. I don't need to be worried about the bond slip law in here, because I already said that the last point is fixed to the loading plate, so no need to activate it at the end. There is also a question: could Hoyer effect in case of pre-stressing bars be modeled? I must say that I'm not familiar what's that. So maybe if this question is from Somar, if he can contact us by email, we will look at it and reply it. Yeah, the next question, of course, it can be modeled for curved reinforcement. And yeah, the next question is from Sinan about the interface properties, about when we model it as a 3D element. This was not actually the topic for us, but also users contact us with this kind of problems. This is usually kind of depending on the model, how to set the cohesion and tensile strength for the reinforcement and how to define the softening function. This is different topic. Maybe we will prepare a separate webinar for some other time. But the general answer for this one is that it needs to be calibrated based on experimental data. Yeah, so sorry for running a little bit late. Again, thank you for your attention. And with this one, we will end today's webinar, and hopefully we will see each other, or you will join some other webinar where Jan will be presenting in the future. So thank you for your attention, and have a good rest of your day. Goodbye.
ATENA program produced by Chervenka company. You can find us via the website and download the program from it, or on YouTube by name Chervenka Consulting, or in Facebook by name ATENA. Finally, we thank you for your attention, and for any inquiries, please don't hesitate to contact us. Have a nice day. Bye bye.